All right. So the big difference between conservation of mechanical energy, or a consequence, one of the big consequences, um, is that momentum has direction where mechanical energy did not. We didn't care which way objects were moving. We just said, are they moving? Okay. Momentum is a vector, so it totally matters. Bless you. Okay. So what does that mean? Here's kind of an example. Correct answer is A. Good with that. Pin has no momentum. The ball has momentum to the right. Total momentum of the system is to the right. So if we put both objects in our system, correct answer is A. Because the total momentum of the system is conserved both in the magnitude and in the direction. The total momentum of the system beforehand was to the right. The total momentum of the system is still to the right afterwards. Okay, good with that. That's kind of just a big general factoid there. Give this a shot. Thumbs up when you have a guess. Talk to your neighbor.
But when that's still yeah, I know. So good if it was going to the right.
There's no unbalanced. Unbalanced would be like, yeah.
Okay, what do you say? A. How are we doing with A? Okay, now what I'm going to introduce here is what I would call a momentum vector diagram. So if I ask for, hey, what is the momentum vector diagram? This is what you're going to do. Now, I completely agree. For this problem, it is over the top, redundant, didn't need it, but I'm trying to take something simple and teach this to you. Okay. So initially, the momentum of the ball was 20 kilogram meter per second to the right. The pin initial momentum was 0. So these are the two objects in our system. So the total momentum of our system is 20 to the right. Good with that? Now, if we discern that momentum is conserved for the system of the ball and the pin, then the total momentum afterwards is still going to be 20 to the right. That's what conserved means. It stayed the same. Okay? So we have some clues about what's going on afterwards as well. Here we have 15. The momentum of the ball afterwards is 15 kilograms meter per second. So 15 to the right plus something gives us 20 to the right. What would that something be? 5 to the right. And that's how much momentum the pin has. Okay? Again, very simplistic. Didn't really need this, but very soon you will need that. So I'm trying to teach you this methodology with something simple. Okay? Momentum vector diagrams. Good with that? Okay. Talk to your neighbor. Okay. Here we go. So we have 200 going to the left, 140 going to the right. Add those together. We're saying that the Maverick and the Raider football players are the system. So the total momentum of the system, therefore, is 60 to the left. Okay. Now, before we jump to the next conclusion about, hey, what's the final momentum total or after the collision, do you think friction is present in this scenario? There's probably friction. I mean, it's real life. But here's the deal. The amount of friction, the size of the friction force is so small compared to the size of the impact force, the applied force, that during those moments of impact, we can ignore the force of friction. Okay, police do this to evaluate crash scenes. They assume that there's no friction during the moments of impact. There is friction between the tires and the road, but the force of the collision is so much bigger than the force of friction that during those moments of the impact, they assume or approximate the momentum is conserved. And it's a good approximation. We're all right with that idea. So yes, there's friction, but during the impact, the force of friction plays such a small role that we can say, you know what, we're going to ignore that unbalanced external force. You all right with that? And if you're on a test, you're like, oh, I don't know if I should or not, ask, and I'll let you know. Yeah, you can ignore friction. Okay, sound good? So after that discussion, do you think momentum of the two players is conserved? If you put both objects in there, both players in the system? Yes. So the total momentum of the system is 60 to the left. Good with that. So B, bountiful buffaloes. Yep. All right. So what I have here, it's going to be problematic. Okay, I've got a 12-pound medicine ball. Okay, standing on this thing. Okay, so I'm going to say the system is going to be the ball, me, and the cart. Okay, what is the total momentum of the system right now? 0. Okay, now what I'm going to do is I'm going to throw this as hard as I can this way. Okay, we know the ball is going to go that way. Watch what happens to me. Okay. Okay, good with that? Give that question a shot. Oops. Tell your neighbor.
And that's the reason.
For the previous questions about like the football players, are we not considering force of gravity and?
Great question. We are, but they're canceling each other out with normal force. Does that make sense?
Try not to do this. It's terrible.
Okay, what do you say? Correct answer is D. Delightful daisies. Good with that? Okay. Couple points on this. First, because momentum is a vector, I can make a distinction between what's going on in the vertical direction and the horizontal direction. Vertically, gravity was a thing. Okay, it was an unbalanced external force acting on the ball after it was thrown. You okay with that? Momentum in the vertical direction was not conserved. But if you just look at the horizontal direction, it is conserved. Okay, so on a test, if you're like, are we looking at overall? Are we just looking at the horizontal direction and vertical? Feel free to ask that. I'll try to define that, but here, I defined it in the horizontal direction. Okay. The other thing I want to bring out is why Like I started with zero momentum for the system, but the ball definitely had momentum afterwards. I had momentum afterwards. How is it that the total momentum of the system was conserved? Because before I had nothing, and then afterwards I had something. My question makes sense? Valid point. Not conserved. I mean, everybody said D, both B and C. What am I failing? What does my explanation fail to take into account? Not conserved. Start with zero. Afterwards, there is something. So I'm saying A. You all said B and C. Why is my explanation wrong? What? How did it cancel out? There, direction. Okay, so total it was zero. This, I'm making this number up. Let's say it went 10, had 10 this way. I had 10 going the other way. Okay, so they canceled out to be zero. Now, how do I have the same momentum as the ball? The ball was going so much faster than me. Andrew. Momentum has a mass factor as well. It's not just velocity, it's mass times velocity. Okay? I would recommend drawing a momentum vector diagram for this one. Talk to your neighbor. Okay, what do you say? All right, so for this, I didn't give you any information for the individual pieces initially. All I gave you was you had 40,000 going up for your total. Okay. There are no unbalanced external forces. The explosion is an internal force. So momentum is conserved, so you still have 40 going up. But over here, this guy now has a momentum of 50. 10,000 kilogram meter per second going up. So 50 plus what? 50 up plus what gives you 40 up. 10 going down. 10,000 going down. See how that works? Okay. Big concept here. On the test, I'm not going to say positive or negative. I'm going to say up or down, left or right, east or west, something like that. It's on you to define which way is the positive direction. And you have complete freedom. You just have to make one of those like one way positive. You could pick different than I did, and that would yield a different answer. But if I stick to right and left, your answer should be consistent if you did the math right. Okay, most people miss these problems because they're not faithful with direction. That is like the number one pitfall for this unit. The math on this unit is not difficult. Okay, you just gotta incorporate direction. Okay, good with that? Sophie. Great question. I should have said deep outer space. Yeah, you should have said deep out. Yeah. So we're going to ignore gravity. Ask that. Okay. I would highly recommend doing a momentum vector diagram for this one. And we are just looking at the horizontal direction. Talk to your neighbor.
About it too hard. Because it has to equal. Both have to be once.
Okay, let me just throw out this point of feedback. If you or whoever you're talking to, if neither of you have done the momentum vector diagram, it is the blind leading the blind. This is not an intuitive question.
So it has to be more
Yeah.
So it's always
Make it. Make it. Okay. So C.
If momentum is conserved. If you're doing this approach, yes. Because if it's not conserved.
Right,
Right.
it is conserved.
It is, yeah. If it's not conserved, then you're doing this approach. But we already learned the momentum changes.
And then replace those.
I don't see what it is. Remember, I don't know.
Are the totals always going to be the same number as initials?
Great question. Not all. I mean, if you're doing this approach, yes. But if you find the momentum is not conserved, then you're going to do this, and I'll hit this as a class. But you're doing what we learned already. So momentum changes, and so you do that route. Does that make sense? Okay. Here we go. Let's see if you're right. So I'm just looking in the horizontal direction. So I've got 1 to the right. I got 0. Add those together. I get 1 to the right. Okay. We're going to put both objects in the system. In the horizontal direction, there are no unbalanced external forces. There's gravity, but that's vertical. We don't care about that. So the total momentum of the system afterwards is still 1 to the right. The golf ball, we don't know how much momentum it has, but we do know what? It's going this way, right? Now, do you think it's going to be more than 1? That would be a really weird bowling ball, like it exploded. Like it's somewhere between 1 and 0. Does that make sense? I'm just going to say 0.5. It really doesn't matter. It could be 0.9. It could be 0.2. It doesn't matter. Okay. So I've got 0.5 to the right plus something gives me 1 to the right. Correct answer is I have to have 1.5 to the right. Correct answer is C. All right. Now, very non-intuitive question. You need these momentum diagrams to help guide your thinking. Okay? Here's why this makes sense. How can you have more momentum than what you started with? Well, here we had more momentum than we, oops, sorry. Oh, yeah. Here we had more momentum than we started with. Here we had more momentum than we started with. Okay? Just saying we have more momentum than we started with, that's not a good indicator. So if the total momentum of the system is going this way initially, then the total momentum of the system afterwards has to be going this way. So if you have something going this way, the other thing has to overcompensate for this way by being more positive or more in this direction. Does that make sense? So the total momentum of the system is still this way. You get that? Okay. Had a couple people ask, will this always be the case? It is if momentum is conserved. If momentum is not conserved, don't do this route. This works well for when momentum is conserved. If momentum is not conserved, that is when you pull this maneuver off here, which you've already done in the past. You find the change in momentum. Okay. All right. So that's what the worksheet tonight's going to look like. We are a little bit behind pace of where I was hoping we'd be from yesterday, so I'm going to forge ahead into lesson 4. So this stuff here is what your worksheet is going to look like tonight. Okay. Lesson 4 is incorporating. We know that momentum is mass times velocity. Okay, so we're doing the same ideas, but we're incorporating this mass and velocity. So here's an example problem. Let's say, going back to our bowling ball, bowling pin example, we have a bowling ball, has a mass of 7 kilograms and initial velocity of 2 meters per second to the right. So we got it's moving slowly. And the bowling pin has a mass of 4 kilograms and initially at rest. Right after they collide, the bowling ball is now going at 0.25 meters per second to the left, meaning it bounced back. So it was, I don't know if you've ever rolled it super slow and like it hits the pins and rolls back. It's like, you got to call the attendant because now your ball's in the gutter. It's not leaving. Like, okay. I want to know how fast the pin is going after the collision. So first thing, I was like, what objects am I going to put in my system? Ball and the pin. So I'm going to say that the total momentum of the system is conserved. Okay, so that's a very general statement for momentum is conserved, conservation of momentum. Okay, so to flesh that out, to I guess put some flesh on this, for this scenario, it's the two objects that make up our system are the ball, so the ball's momentum, and then the pin's momentum. That gives us the total momentum of the system initially. That is going to be equal to the ball's final momentum, the system's final momentum, which is captured by the ball's momentum plus the pin's momentum. So everybody see how this mathematically represents conservation of momentum for this scenario. This is the system of the ball and the pin. We're just adding them up. Now, recognize or remember that momentum is equal to mass times velocity. So the ball's momentum is 7 kilograms times, very important detail. You need to pick which way you want to be positive. That is a mandatory step. I'm going to say to the right is positive the way the bowling ball was going initially. Could make the left positive, but all right, so it's moving to the right. So I need to assign a direction assigned to the velocity because velocity has direction. Now, this is not a requirement to put a plus. I think it's just good practice. But if it's going in the negative direction, if you don't put a negative, that's a mandatory step. Like you will get the wrong answer. Okay. So plus the pin's momentum initially, which is 0, is equal to afterwards. The mass of the ball did not change, and the ball now is rolling backwards to the left, negative 0.25 meters a second. So this has to be included, the negative sign. That is like super crazy important. Minus 3 points on a multiple choice if you forget that one. Plus 4 kilograms for the pin times final velocity, we don't know. Good with that? That's the setup. And now we go and do some math. So we got 14 kilograms meter per second is equal to negative 1.75 plus 4 times final velocity. That's going to be equal to positive 15.75 is equal to 4. And I find that to be 3.94 meters per second. The math says that this is positive. Okay. When you're setting up these problems, if you're given a value for velocity, you must assign a positive or negative direction to that. If you're solving for velocity, do not assign a positive or negative value to that. The answer will incorporate the positive or negative value. Okay? So, do we expect the ball to be going in the positive direction? Sorry, not the ball. The pin to be going in the positive direction? Yes. Was velocity conserved? Well, 3.94 plus a negative 0.25. You started with 2. Velocity was not conserved, but momentum was. Okay, good with that. So that's, this will not be on tonight's homework, but on the next night's homework. Okay, good with that.